Bismillah ar-Rahman ar-Rahim. Welcome back to our course Deep Learning on Computer Vision. Today we are going to discuss the lecture number 22, and it is devoted to practical implementation regarding the deep learning concept, how we can start a deep learning let's say project, and how we can train, modify, test, validate, and then deploy the proposed or the network that we are working on. So let's jump to our lecture notes and slides and proceed further. So the title of our presentation today will be MATLAB tutorial on deep CNNs. The session's guidelines are as follows. We'll talk about in general how to apply deep learning workflow. What are the steps that are to be taken in order to achieve successful results using deep learning. Then we'll talk about deep learning with MATLAB, how we can have a warming up with MATLAB in the deep learning toolbox. Then we'll take some practical and demonstrative examples using MATLAB and see what are the benefits of using different deep learning networks like let's say AlexNet, your own built deep learning neural network, and other networks also as well. So let's go and see now what is the first part of this work is the deep learning workflow. Actually, to start and to get a successful result in implementing the DL neural networks or convolutional neural networks in real-world projects, it requires more than just knowing how to build an ANS or CNNs. We also need to have what we call the workflow to understand what are the steps that we need to take in order to achieve success at the end of our project. Here we have a block diagram describing in general what are the steps that can be taken. Let's have a look on this block diagram. I'll try to zoom it a little bit here. So the first step is the data acquisition. You can see here the left-hand side. So the data acquisition is a very important part as a starting step of the workflow in deep learning design. What does that mean? We need to collect data. Next, we can work on this data by getting this data from public data sets, from databases, from web scraping, crowd labeling. All these things are required to apply as a first step before starting your network processing or evaluation. You need to have a good data set at the input for the training purposes, and the same thing for the testing data set. Next, we'll talk about this later. Next, we need sometimes to apply pre-processing. So in the case of pre-processing, this means that you may get some data and you need, for example, to unify the size of the images or the format of the images. Sometimes you may need to let's say enlarge the number of sample or increase the size. Maybe you need to have a data set with larger number of samples, so you need to apply some sort of what we call the augmentation. So we need to add more samples to our data set. We may need to scale some parts of the images, or for example apply cropping manipulations, image processing manipulations. All these things can be done using the pre-processing step in this situation, and this is the second part of applying the workflow in general for MATLAB and for any other programming tool. Next, if we go to the second next step, we need to split the data. So we have a good data set. We want now to split the data set into main parts. And these parts, as you see here, divide the data set into training, validation, and sometimes test. So the data set must be divided into three main parts. The first part is the training part, the validation data set, and maybe sometimes we need to have the testing data set. What does that mean? We'll talk about this on its time after maybe a few slides. Now, if you have in your data set some problems like, for example, imbalanced number of samples in each class. For example, you have 8 classes and the number of samples in these classes is not very close to each other. The number is not very close. In this case, you need to add more samples to the classes having lower number of samples. And this can be done at this step by applying, after applying the splitting data, you need to again pre-process or add post-processing to this step in order to achieve the required more or less balanced data sets for the training, validation, and test data sets as well. Now we go to the next step. We need now to build or to train the model. Now, according to your knowledge regarding this topic, you now may need to build from scratch your own data, your own model, deep learning model. And you may also use transfer learning from other already available data, let's say the deep learning or CNN well-known popular networks. So you can define the model that you want to use, and you can here prepare your hyperparameters, your initial values for this network, or you can train, you can next go for training on the next step. Now, sometimes you may need to build this from scratch. So you may need to build the network from scratch, or you can use already built using transfer learning other models, after which you can train this model after preparing it for, and we'll see this on the tutorial at the end of this lecture. Once you have trained the network and you are satisfied with the results, you can proceed further and get and try to evaluate your output data set, or sorry, the deep learning system or network. So you can start evaluation of the performance. You can check the accuracy. You can check the other parameters, evaluation metrics like the let's say precision, recall, font score. You can also take into your account the let's say time or the flops required to perform the training and the time required for applying the testing step. All these things can be included in your account, and you can calculate and you can choose the proper metrics. Sometimes some metrics are suitable for a given application while it's not suitable for others. For example, when we talk about the accuracy, it's suitable for classification, but it's not suitable for maybe for segmentation or object detection. You may use other let's say metrics. Now you can evaluate your results using the evaluation dataset, and also you can use this part where we can find it here somewhere. Okay, the test dataset here at the upper left corner here, right corner. So I prefer to do this on the test dataset because usually the test dataset was not used during the training, because when we train, the validation dataset is also interacts with the training dataset, and sometimes it's not a good choice to use it as for evaluation of the performance of your deep learning neural network. Now, if you are satisfactory and accepted, your system is accepted, you can go further. Otherwise, if you get some problems, like for example, you may be having let's say the accuracy is not very high, maybe the time is very long, maybe you get overfitting, underfitting issues, situations. In this case, you may tune the parameters. You can tweak the architecture, and you can modify, add some connections, some residual skip connections maybe. You may add attention units. All these things can be obtained. You can also add regularization. This includes, for example, batch normalization, dropout. You could also add modify the loss function in your system or in your deep learning network. After this process, which is a feedback process or loop type process or analysis, you can see why your model is struggling and is not getting you the acceptable results. And you can now modify, and by applying these changes to the previous blocks before applying the training, and you can repeat the training until you are satisfied. Once you are satisfied, you can now go and deploy your network after that by adding other parameters to make it to consider, for example, the make it as a pipeline, or maybe you can use, let's say, what we call it the industrial issues and limitations that can be faced when you use and deploy this network. However, all these things can be done and step by step. This is the general workflow for any, let's say, design of or implementation of deep learning, CNN, or neural network in general. Let's start with the first step, data acquisition. Here we have to get enough data. The most important part here actually, and is most concerning, is the issue of having, let's say, the most important and pressing concern is to get a good data set, good organized data set. And for this data set, you need to have a proper number of labeled data. So if you are if you are dealing with classes, you need for these classes to have these classes being classified into classes or into folders. In this situation, you need to have for each input what is its class, to send it to a proper class or to a proper maybe folder. And we always have this question: can we get enough labeled data? For sure, this is a big issue, very important issue and concerning issue. And we try to do this by either going to already available datasets, public datasets that are published on the net, like on GitHub or maybe on links in papers. All these things can be also available at different sites. And you may sometimes apply some modification to this data according to your application. So this is one of the important parts of our work. Next, of course, the more labeled data you get, the better the model will be performing, because the larger the size of the training data set, and for sure for the validation and testing, the better will be the performance. And this will give us a smooth and marvelous performance regarding the accuracy maybe and other metrics for evaluation. In fact, this represents a very hard work for the deep learning, and it's the main concern in deep learning networks to prepare a good data set. Now, as I said, we can find this publicly, even though you have to have a look on this public dataset and try to apply pre-processing for that. This will be explained on the next slide. Also, you can collect your own dataset from personal database, from the internet, from some corporations, from maybe you can buy some samples from companies, etc. All these things you can do all this. By the way, we have a good repository which is called the Kaggle. It's an open data set for machine learning projects, which is called Kaggle. You also can find a lot of that datasets on GitHub, and you can find it also all over the internet when dealing with deep learning sites. Also for medical applications, you can find a very large list of freely available data sets for deep learning applications. Now, once you get the data set, you want now to pre-process if required. What we mean by pre-processing? Sometimes you may, let's say, add some samples. You may remove some samples according to their classes and level of accepted level of for your application. Here, the processing must take into account the following things. This includes, for example, the following steps. We need first to clean our data. What we mean by clean? Sometimes you may get some bad samples that are confusing. For example, they may be belonging to a class 1 or class 5. In this case, we try either to correct this sample or get rid of it and exclude it from our data set. You can handle categorical features and maybe add additional text. You can scale or have real valued features using normalization or standardization techniques. So it depends on your input. Sometimes if your input, for example, is a real signal or real valued features, and the span is very high between the min and max, you may apply standardization and normalization. So it depends on your own application. So you need to pre-process this data and prepare it for the next step, which is the training. One of the big issues also in this case is that the number of samples in each class usually is imbalanced. To do corrections to take actions to correct this issue, you may do one of two things. You may apply image processing, for example, in case of images, image processing, adding additional samples using image pre-processing tools like image flipping, vertical horizontal flip, maybe darkening, adjusting, maybe rotation, right, left, vertical, horizontal rotation, degree-based rotation, etc. All these things can be obtained. Also, you can use another network to add to produce new samples. This can be done using, for example, the GANs, the generative adversarial neural networks. And in this case, you can get new samples that are do not exist in previous cases or in the original data set. However, it will enrich your data set and make it more balanced to get a better performance at the output of your network. Here we can use also for signals undersampling, oversampling, by adding extra samples, by removing some samples. This depends on, it's an art actually, and it depends on your choice how to provide this action. It's at most cautioned by expert. You must take care, and with time you will be experienced to apply such applications. The data augmentation, it's a sort of data enlargement. So enlarging the number of samples or increasing the number of samples in each class, for example, or in the data set can be done using augmentation. Augmentation can be done by just simple processing, pre-processing or image processing or signal processing applications or software tools like oversampling, maybe you're done using replication, image sharing, image flipping, rotation, or you can use other advanced techniques like maybe morphology, maybe segmentation, maybe other types. It depends on each situation how we can tackle such problems. Now we have here the dataset splitting. Once you get the full dataset, you can start now to subdivide this dataset into three main parts. The first part is the training set that contains both the training set and the validation set. Now, you can take also a small part of the data, maybe up to 10%, as a testing dataset. This part will not be included during the training. You can use it after training for validation purposes. Sometimes many works are excluding this part and use the validation dataset as the test dataset. I have actually some concerns regarding the issue because when you deal with the validation dataset, actually it has been when you train it, you are going to use it during the training, and it will be with interaction with the trained dataset. So I prefer to have a testing dataset outside your training process, and you can add it after finishing the training, but when you apply validation or further steps. Okay, so the training dataset is used for training. The validation is used to evaluate the progress of the training stage. So you just during the training, because we have a lot of number of samples. For example, sometimes we may get for the classification up to 10,000 samples. So you pick a part of this data set as validation in order to track the changes and the progress of your training stage and the progress of your system performance after finishing specific iterations or a part of your training. While the training data set is used to evaluate the model performance. So we assume that the testing dataset is an outside training dataset that is used for modeling, for evaluating the model itself. And this is why we divide the dataset into these three main parts. Now, building the model, you can go now and build your own model. And this depends on your experience and on your objectives to what you want to get, either to start from scratch to build the model on your own and try to fix and modify every time and improve the quality of the performance or the evaluation of your system. Or you can start, which is better in this case, to take some previously trained model and modify and take its initial values, weights and parameters, learnables, and apply your own input and apply your output classifier to get benefit of the already trained network. This is called the transfer learning. It was discussed in the previous lecture also. Now we can choose our parameters like the loss function and other things. Now, like the hyperparameters, here I have some recommendation for you that you can use when you deal with the hyperparameters. Mainly, you need to pick the initial rate, sometimes between 0.01 and 0.001. You can use or choose the regularization method to regularize the output by the feedback propagation or by applying many issues like to take the N1 or L2 regularization. You can apply also data augmentation to avoid overfitting or underfitting. You can also, when you see that the system is not going further to be improved, you can stop and use early stopping somewhere, and this is very helpful. You can also select change the loss function. You can use here SGD, SGDM, Adam optimizer. All these tools can be found within the software or when you program your own network. You can also select the batch size, which is the mini batch size. The mini batch size here is related to the number of samples that are batched together as a mini batch for applying the validation tool. Now, the larger the size of the mini batch size, the better will be let's say the feedback taken from the network, and you can use this as a good indication. But when you increase the size of the mini batch size, you will get let's say higher computational cost, and you need to have a compromise solution. We usually take a mini batch size between, let's say, 16 and 32. Anyway, you can select higher or lower, depends on your facilities and your purpose of using or designing this network. Once all these things are ready, you can start your training and proceed further. You train your network, you wait until you get a trained network. Next, you can now apply the evaluation of the model performance. This can be done either on the validation dataset, as usually done in most cases, but I prefer actually to apply the evaluation using the testing dataset. Now, if the validation dataset was fed to the into the computer or in your program, the MATLAB and other softwares can also handle it and apply the evaluation at the time of the training. And this is from one side is good, and from this other side it will be a little bit different from the when you apply the dataset from the testing dataset. Now, you apply the performance evaluation according to the validation or testing datasets. This will give you a sense for how the model will be performing for new unseen data. I think in this case, this is why I need to use the test dataset as the samples that are not seen by the network before. And this will give us more generalized, let's say, overall judgment of the performance of the system. Now you can measure how you can evaluate your performance by measuring the accuracy, the phone score, the precision recall, and other, of course, other evaluation parameters depending on your purpose of your system. Here is a good link that you can find many deep learning projects with source code. The InterviewBet website. I encourage you to have a look on this link and get some knowledge from there and get some examples, very useful examples. Now you get some problems with your system, and due to that you have to modify your tuned parameters. You may change the learning rate, the minibyte size. You may modify the architecture. You may also add regularization techniques like batch normalization. You can modify the augmentation, add samples, remove samples. You can all these things can be done to avoid either overfitting or underfitting of your data or your system, deep learning neural network. You can actually, in order to avoid such problems, you can start with a smaller model. So it's a mini data set, and scale up step by step to get the best performance. This is done to avoid the overfitting issue. Actually, there's no guarantee on that. However, I will show you in next few minutes some MATLAB tutorial that starts with a small-sized data set just to save time and your time and my time in explaining the deep learning implementation in MATLAB, which is very strong and very simple for you. I hope that you'll enjoy it. So for now, we can go and if you are satisfied with your results, you can adopt and deploy the model. This includes additional information like the industrial background, how to convert your core software into a hardware implementation, maybe the computing requirements, the acquisition of the inputs, programming facilities, the memory available, the processing speed. All these things can be included and can be taken into account in case you are requiring or you are tending toward deployment of your model. For now, I think we need to jump and go to MATLAB and see what we can and try to, let's say, type here or there and drag and drop some blocks in the, let's say, deep neural network or deep learning toolbox. So let's go there and have fun. So now let's go and open MATLAB. You will have such a page. Now for this case, you can select one of two options to open the Deep Learning Network Designer. So either you can press on Deep Network Designer here and click Enter, or you can go also through the apps, and here as you see the scroll bar, you can just drag scroll and go to the Deep Network Designer. Here, same thing, or if you click on one of these, on this knob or on this button, or you can go also during or via or through the MATLAB and click enter to see what will be what will open for us. So let's click now on Deep Network Designer command line and go enter. You'll see that this will open for you the Deep Network Designer. It's an empty. As here we have on the left hand side, we have a group of layers, a library for layers, and we have an open free page and some details here. We'll talk about it later on. Now, before going and continuing in MATLAB tutorial, we need to prepare our dataset. For your convenience, I will include with this lecture at the lecture 22. Here if you go to lecture 22, you can see a MATLAB folder for lecture 22. If you double click on it, this will open some MATLAB files, and here we have classes for 4. So this our dataset called I call it classes for MP. Double click on it, we can find two mini datasets. ELPV dataset is a well-known dataset in the field of PV panels in electrical engineering. If you click on it, you can see here, I have divided the dataset into two subfolders. One subfolder is for training. Here we have 4 classes. If you look at the class 1, for example, let's zoom these images. Let's view, for example, very large icons. If you look at, double click on this one. If you see this image, looks like it's a PV cell with some distortion on its on the plane, on the face of the PV panel. Maybe for you it will be some errors, but maybe it is classified as being with very low error. Now let's continue seeing other images. If you go back to the, here we have a lot of images. As you see that we have here about 100 images. Of course, this is a very small data set, mini data set. What are these images? Actually, these images are the ELPB, electroluminescence imaging data set, generated in 2018. In fact, in PV cells, just about a small background for you. In PV cells, when you apply sunlight to the PV panel, the cells will convert the light into electrical current. Now, if you apply the opposite, if you apply an electrical current to the cell will be shining. Now, you can take very accurate cameras, specified cameras too, in a dark environment usually, to see what are the problems that may be inside the cells. And for example, let's go and I'll show you in class 4, for example. You can see the errors here. So for example, for this image, you can see that we have a very big, let's say maybe we call it black hole or very big error here. This part is having distortions or problems, while most of the other parts are not very seriously damaged. Maybe this we can call it as a crack. Maybe it's a small micro crack. All these problems are studied, and according to the level of distortion on the face or on the plane of the cell, the output power generated from the cell was divided in this dataset into 4 types. The first one So we have, let's go back to the classes, maybe here, back, let's see class 1. For class 1, the power loss for these images was assumed to be very small, so the power loss almost zero for this situation for class 1. For class 1. This was measured and tested regarding this issue. Now for the class 2, there was about 30% power loss. If you look at these images, of course, we have many samples here. We have about 100 samples. You see that we can change all these samples and so forth. You can continue. For the third class, we have the distortion up to 70, maybe 67 or 66.66 distortion results or the power loss. And finally, here for the class 4, the loss is almost 100%, so above 70% and close to total loss. You can see these images if you can look at the images here. For example, if you have a look on this one, you can see that there's a lot of broken parts, and it is expected to have a very high power loss at the output of this cell. So what we have here, we have 4 classes. I do not take it in serious account the type of PV type or ELPV type. It's just a sort of, it's an example for your convenience. Now, the original samples, if you go with me here for, let's see, for the data sets, you can see that, for example, for the LPV data set, we may have, let's have a look on the original one. Here, if you look at the trained data, you can find that, for example, for class 1, if you look at the number of samples here, we have a very large data set. For class 1, we have, if you look here at the corner, you can see that about 2,000 here, 2,173 samples. In fact, this dataset was not as large as this number, and it was not balanced. I tried before, as a preparing stage for my work, to almost take a balance. For example, it contains 2,000. If you look here at the corner, the bottom left corner, 2,146. It's better for all classes, and the number of classes in the original dataset was not as high as this. And here we have 2090. I used data augmentation by adding different types of, let's say, image processing tools like flipping, rotation, adjusting, contrast change, brightness change, rotation of different angles, all these pre-processing, just to increase the number of samples in the original dataset. However, in our case, for this tutorial, we just need to have our simplified or mini dataset, which is, let's see, this one. Okay. I think it's somewhere here. No, let's go to, yes, here. This is our dataset. Here I also prepare 2 types, one with the size 224 and one with the size 227. You can keep it, or you can also just select one type, and then MATLAB will automatically resize the input images to be having your selected size. Now let's go back to MATLAB. So we have already opened here the Deep Network Designer. This will give us something like this one. Let's have a look before starting with a specific example. Let's look at the library. Here you see that you have a library. In the library, you can find or see input layers. You can see convolutional and fully connected layers. You can go further. I'll try to combine all these together. Okay. And see here, we can go further and see for all these layers. You see, we have here convolution, sequence, activation, normalization, utility, drop out layout, scaling, quadratic layer. All these layers can be found in MATLAB pooling, different types of pooling, two-dimensional, three-dimensional, maximum, global, etc. We can find also a combination, addition, depth concatenation, concatenation layer, multiplication layer. All these layers are very important in building your own. You can find also for object detection other versions, for example, for ROI max region of interest pooling. You can find YOLO versions. We'll talk about this later on. Anchor box layer. You can design your own system, your own from. In fact, it's very rich library having all these, let's say, layers or blocks for your convenience. Now you can continue until you reach the output, which contains the softmax layer, sigmoid layer, classification layer, regression layer. All these things can be found here. Focal loss layer, when you use focal loss instead of the in the loss that is usually used like in classical methods. Let's now start simply by building a small network. Let's take an image input layer, just drag and drop. You can double click now and select the size of the image. Here we have 227 by 3. You can change this as you want. Now you can now add, let's say, a convolutional 2D layer. We take a convolution layer. Also, we can take as a result a ReLU layer, activation function layer as ReLU. We can also take, let's say, batch normalization layer. If I think it's not required. Anyway, you can also add it. And finally, we can get the output, let's say, maybe softmax layer, okay, and the classification layer. These layers are enough for me to generate or to build a neural network. Now we can connect these layers by just clicking with mouse click here. You can connect this one this way, can connect to the this way, renew, and connect again here, and sequence or cascaded building of the unit. Now you are not satisfied with the outlook of your network. You can just apply auto arrange here. You can see this at the upper left corner here. Here you can see auto arrange function. Auto arrange. Okay. And just click on auto arrange. You get the system more or less arranged. Now you can zoom it plus control plus or control minus and select control plus to zoom this network. Now, of course, I'm not sure that this network will be working very effectively. Anyway, this is the input layer, or the input or the design of a simple network. Now, we can modify for everyone, for example, for the convolution. You see here, if you look at these parameters, you can see various things that can be modified. Here you can change the filter size, and you can change the name. For example, convolution step 1 or layer 1. You can change now the number of the kernel size, let's say 5 by 5, for example, or 3 by 3, etc. You can also change the number of filters. You can keep the number of filters small, 16. We can also make it 128. It's up to your choice and depends on your design. We can change here the stride. If you have a look at this one, here we can change the stride. Also, we can change the dilation factor. Okay, when we use dilation convolution or dilated convolution, you can change the padding. The padding value, it could be 0, something else. So all these options are available for you in MATLAB and can be done in a very smooth, let's say, graphical user interface. You can change the weights, the bias, etc. All these things can be done for all. The same thing is true for all other layers according to their parameters. For example, the softmax layer, here it's a softmax, here the class output layer. If you click on it, you can define now the number of classes for in the softmax layer. You can change the name. Now you have already this network, and you can now go to analyze. You can go and analyze your network as here on this scroll button, and you can do this by just analyze the network. So you can analyze, and the network will be starting. The deep network designer will analyze for you the system. So this is the result of analysis. You see that we have some problem here where we can see the class output, invalid input data for classification layer. Input data must have special dimension size equal to 1. So you can now follow and see every single component in the layer, and here, and you can see that if we zoom it a little bit, is the input image layer. Number of learnables is 0. Commission 1 3 by 3. Number of filters is 32. The bias is also the same, and ReLU. The output now, the bias normalization, the softmax output. Now we can modify the softmax in order to correct for the class output. Here we need to make some corrections to correct the softmax to define the number of classes in this network. So we need to go back again to our network and see what can we do for in this situation. Now you can also go to the data. Again, this is the designer. We can go now. Let's try to show you the data. Okay, here we can see the data, and here we can see the training step of the model. To avoid such problems, we now try to go and use what we call it transfer learning. I have already loaded a network on my MATLAB deep learning designer. I can go to the new window, as you see here. Here you can go to this new window. Okay. And click on it to get what we can find there. Just a moment. Yes. Okay. This is new. You can go now and see what is available in MATLAB. You can start blank as we just did, and you can take the network directly from the workspace where you can get this network, or you can go also and see the many pre-trained images. For example, we have here a list of pre-trained images, like pre-trained networks. We can see SqueezeNet, GoogleNet, ResNet, a long list of networks that were trained in this regard. Now you can see that here, this is SqueezeNet. Because we don't have this triangle, it means that we have already loaded into our system. Now we continue our work on other networks. If you are interested, for example, with DenseNet 2001, ResNet 18, here we have DenseNet. You see DenseNet is very important and new topic. ResNet 18, we discussed this in the previous lecture. Inception, ResNet, VGG 19, VGG 16, and AlexNet. Now, in MATLAB, you can now download. You can click on this command and download for example, AlexNet, you see that pre-trained AlexNet network, depth 8, size 226 megabyte, parameters 61 million, input size 227 by 227 by 3. And if you click, you need now to pay for it. In order to avoid this, you can, of course, if you download this network and install it, you will be able to enjoy the parameters, the trained parameters, and take it as pre-trained network. Now, to avoid this problem, at least for today, we can load, let's say, AlexNet. I think I have already escaped. Yeah, you can call the AlexNet with having their weights as untrained weights, and this will load for you the network AlexNet. Let's click on it and see. Now we have already at the, if you look at this corner, the workspace, you can see many networks. One of them is the AlexNet that I have already loaded into my system. Of course, here I can double click on AlexNet here and see what is inside the network. I can have it as a 25 layers. Now, as you see here, we have, these are the layers of the neural network. All these layers are built in the AlexNet. Now, we can go back to the deep learning designer. Let's remove this one. Okay. Okay. And let's start a new, let's say, a blank, or maybe from workspace import. If you look at what is will be shown now, you'll get all the networks that are given on the network on the workspace of MATLAB. In this case, I will select. I will start with AlexNet layers. This is the same as the AlexNet, but with no previous training. Yes, I want to replace this window and get the AlexNet. This is our pre-trained, maybe not in this case, not pre-trained because you need to pay for extra for having the network. In the previous versions, you can find it without extra, for free, without extra payment. Now we can zoom Control Plus. We can see all these layers in the AlexNet. So this is the input data layer. As you see here, we have the image size 227 and by 3. The face convolution layer 1 by 1, 11 by 11, and number of filters is 69. Here the stride 4 by 4. ReLU layer, normalization. Here this is cross-channel normalization. Pooling layer, max pooling, convolution 2, etc. You can find all these steps that we discussed in the last two lectures, and we get finally the fully connected layers. This is 1, and we continue until we reach three fully connected layers. And here we have softmax layer that combines the probabilities of the fully connected layers, and the output that defines the number of outputs in this case. Now we need to train this network. We assume that if we analyze the network here, click Analyze, you will see that there is no problem with the analysis. So you can see here by the analysis that we don't have any error. Here, this is on the left-hand side, the network itself. And on the right-hand side, we have here all these parameters and with specific activations, learnable properties, and until we see and check for all these points. And here we can see, if you noticed, here we have this window or this icon, or maybe that we have 25 layers, we have 0 warnings, 0 errors, and we have the total learnables about 61 mega learnable parameters. Things looks fine. Okay, it's okay. Now we can go and proceed further in our training. So we need now to fit or to upload our data. We go to, let's go back. So we are actually going to this, just a minute, just to pick for you, yes, this drawing. So we can go to this data window to apply our, to upload our data. Now, you see, we need to upload our data. Here, this can be seen from, can be uploaded from here. Okay, so let's import our data, import image data or data store. For us, it would be possible to do one of the two things. The first one is by folders, and the second one by data stores, a sort of formatting for data sets that can be used, and you can explore its importance. Now, you can import data training for training. You can import the image classification data for training. Data source, a folder. It could be image data store in workspace. You need to load it to MATLAB then as an image data store format. Or you can go and select a folder. Let's go and browse the data set. In our case, here this is the data set. I need to here to upload the 227 sized data set and go to the train folder and select folder. This is the folder. Here you can add some augmentation options by random reflection, rotation, rescaling, translation. All these things can be done. Now we go to the other part, which is the validation data. Here, and as you see, here you can find that split from training data and the percentage of this split. So I can now either select from split from the data, or I can select a folder. Actually, in my case, I used to combine the validation and the training data set in one file, in one folder. Now, the percentage now of how much is the validation data set for, in this case, I can replace this by, let's say, 15%, because I have the data set outside the, from outside. So let's say 15 for the data set, for the testing data set, and maybe 15% for. So I leave here 85% for training and 15% for validation. Now, for testing purposes, I already included a file or a folder with every class. For the train, for example, here we have these classes. If you go back, you can see the test data. And in this case, each class contains almost, if you see here, you can see that we have here 15 samples. So 15 images in this case. And 15, it's about 15% of the 100 images used for training. If you go back here for training, you can see that the number of images here, if you select, if you look at the corner, we have 100 items. So this is a very small data set. Usually we can use hundreds or maybe thousands of samples to train our system. I have done this in order to show you the performance of your system. And now we are ready now to import this data, and let's see what we will get here. So this is the imported data or uploaded data for training, and you can see now. Let's remove all the let's clean all these things here. Okay. Okay. If you look at this graph, you can see the number of classes is 4, and you can see also that the number of samples is about 85%. because we have 100 samples per class. Of them, 15% are for validation and 85% for training. And this is why we, for the training data set, we get this number of samples. You can go now to the right corner here, you can change the training to validation and see that we have 15% of, otherwise we have, let's say 15 samples per class for class 1 to up to class 4. So let's go back to the training. Okay. Now we go to train. So our network is ready. Our data set for validation and for training is ready. We can go and press on this button for training purposes. And let's do this. Let's go and do training or start training. Before starting, we need to specify our hyperparameters and modify or maybe changing the training options. You can see here we have to change the training options if we wish to change, or at least accept as is. So it's a must to go and click on the training options. Okay, let's maximize this window. So here we can see a lot of parameters and options that can be done. The first one is the solver. Here we can use the SGDM solver, or we can modify by selecting, for example, Adam or RMS prop. So this has been discussed in details in previous lectures. So we usually take SGDM, stochastic gradient descent with momentum. Now we can select the initial rate. So we can select the initial rate. In this case, we selected the rate as 1%. We can modify it to make it 1.001 and continue. Now the validation frequency, how many times you need to provide the validation. You can take it as, for example, as 50. If you modify, you can reduce sometimes this number to make the validation more repeated, to be repeated more and more, or higher with higher repetition, and this will you can make this one by let's say selecting 30, let's say 30 points every iteration. And next we can go and select now let's remove all these things here and to show you the best. Okay, if you go now to see number of maximum epochs here, you can see that we selected number of maximum epochs equals 30. What is the epochs? One epoch means that you have run all the input data set during one stage. So the number of iterations is equal to the number of elements in the mini batch size. How many times is to be repeated until we finish all samples. We have, for example, 1,000 samples. So we need, for example, if we take a mini batch size of 20, we need to repeat this process 5 times. And so we need 5 iterations to continue or to finish one cycle of the embedding of the loaded or the embedded data set. In this case, we have one epoch. We can repeat this process many times in order to add more steps or epochs. The higher the number of epochs, it is usually expected to have the better the performance. And usually we take it for trained systems between 13, 15 and 25, up to 30. For other untrained, we can pick up to 100, 200. It depends on you, on your system and your choice. Now, the mini batch size. Next, the mini batch size Here you can select it to be a little bit. Here you see 128. Let's reduce this number to 16 to speed up our process, because the lower the number, the higher the speed, and maybe the lower little bit the accuracy. You can change it as, for example, let's say put it as 16, a small value. You can continue for all other parameters. What we can now keep here, I think that all the other parameters are already set. You can apply, you can see in MATLAB what are these parameters, what can we can modify. These are all used as a sort of hyperparameters, and you can modify it. Here the momentum as a last step of our discussion. Here the momentum is usually the beta parameter is the momentum, or the temperature is selected to be 0.9. Finally, we can go now to the close window once you are satisfied with these inputs, and you can just close and prepare for training. Before training, let's remove all these arrows and boxes from here and start our training, and just click on the train window here, this green triangle. So let's go and train. The training will start very soon. Oops, we get a problem here. Training with training network failed. Why? Because as you can read here, invalid training data, the output size 1000 of the last layer does not match the number of classes of the response, which is 4. So your input dataset contains only 4 classes, while the output size in your network is just 1000. So there's a mismatch in the what we can do now. We click OK. We go to the designer and go to the fully connected layer here. As you see, we have, of course, I did not go to the output because it is auto. The output size is set auto. If you look at this point, it's a good error because it helps us to see what we can do. So here we have the output size as set as auto. If we go again for the softmax layer, we'll get the same thing, auto. So what if you go now to the prop, there's nothing to modify. Let's go now to the fully connected layer at the last layer. So in this case, we are applying transfer learning. So we modify the input. The input was already set properly, the same size, and this is why I forget to change the number of classes at the output. And this was good, by the way, to help us in correcting or in following our steps in this work. As if you look at the fully connected layer here, you can see that the number of classes are as here shown is 1000. So what we can do now, we just need to simply modify this number and set it to 4, because in our case we have 4 layers, or sorry, 4 classes. Okay, done. It's okay. Now we go to the training stage. Let's remove just the these comments from here and go and apply training as usual, so we can start training. We need to wait a little bit. As you see here, we have 2 curves. The upper curve is for the accuracy, and the lower curve is for the loss or the error. And on the right-hand side, you can see some details: training iteration from 1 to 630, training time, training cycle, validation. Other information can be seen For example, in my case, this computer has one GPU. If you look at this extra information, the learning rate is 0.01. Learning rate schedule constant. We can modify it to make it other type. And the hardware resource here in this computer is we have one single GPU. And during my talk now, you can see that there is a processing that is going by having two curves, one for validation, one for training. This one is for the training data set, and the other one here for the validation. We'll see this in details now. If you look at here, I will remove all this. So here we can see that the smooth line is for training, and this is for the training performance. And the dotted line with black colors is for validation. It is regarding this curve. And when we talk about the other curve here, we have the losses. As you see here, as we move further, there is the improvement is not very high, and the performance is not acting very well. Here we finished one epoch. Every epoch means that we finished all samples according to the selected mini batch size. And I have selected the number of epochs to be maybe 30. We'll see this later on. We'll wait until we get some results. Of course, the number of samples is not high enough, and the number of samples is 100 only. Doesn't reflect actually the variation or the variety of errors in various classes of the network. And as you see here, that the performance is moving further and further, and there is not a big improvement in performance. It sometimes reaches 40 and goes below, and is varying according to the iteration under consideration. As you see, with increasing number of iteration or epochs, the improvement in the accuracy is not very high. I'm not satisfied with this result. I can stop somewhere. Here we have a button, as you see at the corner here. This is the button where you can stop the learning or the training. So let's click on this knob or button and stop training. It takes some while to stop the training. Okay, so our final results are, as you see here. The validation accuracy was only about 25%, which is a bad result. Here, 25. It has been stopped manually. The time used for training was 4 minutes and 35 seconds. Number of epochs just 12 out of 30. And this will be reflected on the iteration by when you multiply 12 by 16 to give you 12 by 16 will give you 248. And you see that the learning rate is very high, little bit high. We can modify the learning rate and go back to the learning options or training options. Here we go to training options. We may change some parameters. Let's say we can change the learning rate to make it very small, 0.001. This will take more time. and maybe we may change the SGDM by Adam. Let's keep it as SGDM. Validation frequency, let it be to be 20. This will not change the ideal. Number of epochs, let it be, for example, 20. And the minibyte size, 32. We increase the minibyte size. What we can do also, we can now, I think it's okay, and close, then train. Discard these results and retrain again. The process will be repeated for training. We'll wait for a while. You see, we changed some parameters and the results are also changing. We'll see if we can get good results for this case. So after the first epoch and second epoch, we see some improvement in the evolution of the accuracy or the training stage, and we'll be waiting and see what will happen after a few stages or few iterations and epochs. So as you see now, after a while, after passing few epochs, we get better performance and we are approaching between 70 and 80%. Now, in order to save time and to make it efficient, I think the lecture is very long actually. Let's go and see. I have one published paper regarding this issue in the Advanced Engineering Informatics. It's a Q1 journal, prestigious journal, having its percentile about 93%, which is considered as one of the good or the very good journals in Elsevier. Here, the paper was tackling the issue of PV panel or PV cell, as you see from the title, deep learning-based automated defect classification in electroluminescence images for solar panels. Here, I talked about previous work, of course, done in papers. Here, the AL imaging setup, how we can apply or get from the PV device the ELPV images or EL electroluminescence images. Also, here we have some examples on images with monocrystalline and polycrystalline type. Of course, I used other type of classification and details on these classes. This is the original data set. I see that for these classes, it's very clear, it's unbalanced. Number of samples in each class. For example, for class 1, we have 85%, while in class, let's say class 3, we have just 4%. Usually in class 1, we have the normal or the good samples. And this is because in life, not the errors are not very high in systems. And it may be, in this case, we have 42% of problematic cells. Next, I have applied augmentation and get improved ELPV dataset with almost 12% of every. I have applied augmentation to balance the classes in the dataset. As you see here, we have almost 12 or 13% of the total dataset is balanced sub datasets or subclasses. Here, I proposed this network with parallel combination of different types of convolution layers, and then combining the result. In the intermediate stage, we have something like, if you look at this image here, block diagram, and in between we have max pooling divided, the output will be applied to 3 convolution, let's say, branches, and then we combine the output and get the last stages, the output. Here we have some details about the parameters in the system, a number of learnables, activations, etc. So Here, the description of the network. And here we have the results for different types of networks. The first one is ResNet 18, ShuffleNet, and we have also another CNN, which is built from scratch, as I just described and told you about it. Here we have for the precision, for the recall, accuracy, all these parameters are given here. Also we have the what we call it the confusion matrix. Yes, I think we have some examples here for different classes, 4 classes, 8 classes. This is a larger confusion matrix for 8 classes. And here the evolution of the accuracy. As you see that the accuracy for the testing, for the training dataset and for the validation dataset are very close to each other. And this is the error. It's another example also. This is what I was trying to show you. And you can continue this paper if you want. I can send it to you and to have a look on it. Let's go back to our MATLAB. As you see here, we have reached very high value during the training. We are almost done because we, we defined the number of epochs about 20. And now our data, our network is ready. Our network is ready. And the accuracy obtained, as you see here, it's about, if you look at this corner, the accuracy will be 93%, 93.33, which is considered as a very good result. Of course, the dataset is small, and this performance cannot be generalized. We need to work on larger datasets, as I have shown you few seconds ago in the paper. Next, what to do now? You can copy this image and keep it in your on your computer. You can now export, as you see here. If you look at this, I'll try to show you using an arrow. Here, you can export your system from this button. If you click on this button, you can see export the system with export trained network with results, generate code for training, export to Simulink, and create experiment in the network DNN experiment. Sometimes you can, in MATLAB, you can train, let's say 4 or 5 different systems with varying only the parameters. Like for example, the learning rate, we took a value of 0.01, then we changed it to 0.001, and we get better performance. You can give instructions to run the training many times using the experimental deep network designer. It's an app in MATLAB. Of course, we are not concerned with this part for today. And now we can export the trained network and results and see what we can do. This will keep for you the initial values, the link to the parameters at the input stage. All these things can be found there. Now, you can also export training plots, these plots that you already have trained, and get it in your system. Now I want to go back to the designer, Okay, maybe we go back to the to the training unit and export as a first step, and export our train network and results. It has been exported. As you see here, it is exported to the train network has been exported to the workspace in having the name trained network 1 and trained info structure 1. Okay, we are done now. Let's go and see our workspace. Here we have the trained network. If you click on it, let's remove all this denotations. Okay, you look at this, you can see the layers. click on the layers, you can see the layers in in this network. Okay, you can also see the input names. What is the data used in this case? Now you can see the output names. Okay, what else? We can go to the info structure, train info structure. Double click, you can see the training loss, for example. This will give you the loss for every epoch in your training. As you see, for the iterations up to, let's go to the end, to every iteration has the training loss. You can see also, you can pick here the training accuracy, 200 points. You can go also pick validation loss, accuracy, final validation loss, final validation accuracy, which is 93.33, and this gives you full information about the training system. Here you can use also to add some. I included in the folder also the file that is created to apply testing. Here the input dataset path. This is the test path, and here we load the network, which is called trained network 1, and apply splitting of the data into validation, training, and testing, and provide with apply the testing. Now we load the test data set and try to find the confusion matrix, the other parameters. You can use it freely. I will provide you with this file, and you'll find it on the same folder of the lecture 22, and it will be very helpful for you. But before starting with the run, let's go and have a look on the designer here. If you don't want to work in form of block diagrams and you want to apply modifications, you can export the network to a file. So generate code. You can generate code for your block diagram or your network. So let's generate this code. Let's generate live script for live editor, so you can here see some information, create the deep learning architecture. Here it will tell you about the number of layers, number of connections. Here the layers that are embedded or included, etc. All these things can be found. Plot layers. Now, in order to run this as a simple code, you just need to save it as, save as, and select .m file, .m MATLAB code file. It's okay, and I already saved this as my net1, and this is the code that will be generated in this situation. Now I have added this line. Actually, the layers will be the network itself, and I called it here my net equals layer, graph, layers, etc. Okay, and plot this graph layer. Now we can run this code. Let's run this code. If we come back again from another time, we can run. It will give you the overall network, and your deep network designer will be able to contact and to load this network. Let's go now and see new, and here we've picked from import from the workspace. As here we have AlexNet. We have also other nets like MyNet with 15 layers. Okay, let's go and see. Okay, this is our network. Replace. Of course, in this case, the network is just for demo. I mean, without initially being trained. So you need to repeat the training from scratch for in this case. While in the trained network that already obtained from MATLAB here, this network already has its own parameters, and you can assume that it's already trained network. Okay. Now, as a final step for today, I think it's a very long lecture, but it's a very, I think, very effective for you to start with a MATLAB tutorial in Deep Network Designer. Actually, I took a lot of time when I started this work because I couldn't find that time proper tutorials on MATLAB. Now, for this code, I can just run. Let's run the code and see what will happen now. So run. So when you run the net testing evaluation, you'll get the results in the form of confusion matrix for the validation dataset and for the testing dataset. You can see the code and follow these functions. Here you can see that the accuracy of the validation dataset is 73%. Here we have this for the testing dataset or the validation is 93.3. And for the testing dataset, as this is very important now to see that it was 73.3, and this will give us some information about the confusion matrix for validation and for testing. As you see here, for validation, we obtained a very high value. Yeah, this will be the overall is 93, while for when we deal with the testing, of course, in case of the testing, this value will be lower. It will be 73, almost 73.3, which is not high as the accuracy that was obtained in case of the validation dataset. Also, you'll find in this code test metrics table. This includes information like here we have the first give you the accuracy for the classes, class 1, 2, 3, 4, then the precision, then the recall, and finally for the Afon score. This matrix is already, I think you'll find it somewhere in here in the output. I think it was a table. Okay, this is the table. Double-click on it, we can find the parameters for every class, including the accuracy, the precision, the recall, and the Afon score. I think by this we reached the end of this lecture. I'm sorry for being very to make the lecture very long, but it's actually it's necessary for you to understand and comprehend the ideas behind the MATLAB tutorial for deep learning neural network, and I hope that it's very useful for you, and this will be a part of your final exam. Hope seeing you soon, and for today I think it's time to leave. And you can go to these links now and see some tutorials and prepare yourself for the final exam on this issue. That's all talks for today, and hope that you enjoy this tutorial, and hope seeing you soon, inshallah. And for now, it's time to leave, and Assalamu alaikum.